This lesson is on direct variation. So far, we have learned about three different types of direct variation. The first type we learned about was linear direct variation. The equation or the sentence is going to look something like y varies directly with x. It might say something like the distance varies directly with the time. The variables are going to change, but it's always going to say varies directly with and then give you something else. The equation can take two different forms. It will either look like y equals k times x or y divided by x equals k. When we look at the graph, it needs to be a line because this is linear direct variation, and it needs to pass through the origin, which means its y-intercept has to be 0. You notice when you look at the equation that there is no y-intercept, or that the y-intercept is 0. The second type is quadratic. A quadratic phrase is going to look something like y varies directly with the square of x. This equation looks like y equals k times x squared. And the graph that you're going to get with that is a parabola. When k is positive, your parabola is going to open up. When k is negative, your parabola will open down. And then the last type we talked about was cubic. This is when y varies directly with the cube of x. So we get an equation that looks like y equals k times x cubed. And then you get this cubic graph here. You'll notice that all of them involve multiplying the constant times x. What changes is whether or not it's x squared, or x cubed. One of the things you'll be asked to do is write an equation for a situation. This says the surface area of a ball varies directly with the square of the radius. When we look at these problems, we first want to look for what kind of variation it is. This says it varies directly with. When we see that phrase varies directly with, that means it's going to be equals k times, because we're looking for direct variation. We want to know what varies. So we look at the beginning of the sentence. The surface area of a ball varies. So it's the surface area that's varying. And then we look at what does it vary directly with? Well, it varies directly with the square of the radius. Because we see that square there, we know it's the radius squared. So first we write what's varying, surface area. So surface area varies directly with equals k times, and what does it vary directly with? The square of the radius. So that's r. The next one says the number of watts of power generated by a windmill varies directly with the cube of the wind speed. So what varies? Well, it says the number of watts of power. So the watt varies directly with equals k times, and what does it vary directly with? The cube of the wind speed. So s cubed. The watts vary directly with the cube of. This problem says the height reached by a pole vaulter varies directly with the square of the speed of the athlete when the pole is stuck in the ground. When they give us a sentence like this, we want to pay close attention. It says varies directly with, so we know we're talking about direct variation. It varies directly with the square of the speed. So we know this is going to be the direct variation with the square of the variable. And we want to look at what varies, and it says the height reached by the pole. So our equation is the height equals k times varies with the square of the speed, s. So we're going to start out with that equation. And then it tells us if one pole vaulter reaches a height of 16 feet, okay, that's the height, with a speed of 32 feet per second. So they're giving us height and they're giving us speed. If we have those two variables, we can find k. Then it says how high does the second pole vaulter leap with a speed of 35 feet per second. So for the second pole vaulter, it only gives us s and asks for the height. We can only find this if we know what k, our constant, is. So our first step is going to be to find k. And then once we do that, we can figure out how high the second pole vaulter is. and we're going to input the information we know. He reaches a height of 16 feet with a speed of 32 feet per second. So we put in 16 for the height and 32 for the speed. Then we go ahead and square 32. It's 1,024, and then times k is just 1,024 k. And then to solve for k, we divide both sides by 1,024. And we get k is 164. Now, at that point, if you want to change it to a decimal, that's fine, or you can leave it as a fraction. Just be sure not to round until the end of the problem. That decimal is kind of long. Okay, now that we have the constant, we can work on our second pole vaulter. We know that he has a speed of 35 feet per second. So we're going to go back to our original equation, and now that we know k, we're going to input 1/64 for k, and we know their speed is 35 feet per second. We're going to plug in both of those pieces of information. Order of operations says we have to do exponents before we multiply, so 35 squared is 1,225, and times 64 is about 19.5. And so our second pole vaulter will jump to a height of 19.14